news what I have for us. Because of King George, I was able to upgrade our whiteboard.fi, so you're no longer going to have a different code each time. So if you get the code down one time, it's going to be the same for the rest of the year. So I know you don't remember. That's fine. I'm going to do that with you right now. So let me share my screen. Okay, admit Cal. And then let's get into our whiteboard code. Let me show it to you. And there we go. Go ahead, join in.
Like, they would never even, not even. They don't, I don't think they know the. They know the. They don't. They're definitely not. They're not. You give me that. I got it.
Yeah, Charlie, can you explain half the words? You spell them.
Can you describe me? Hey, can you? Yes,
Yes, I can.
Can you?
Why not? I can't because I don't like that.
I mean,
I can't stop, but I have to start it. You wish you were feeling like
oh,
shit. It's time to do battle.
We are on Zoom waiting if you can join in.
Okay.
Okay. Let's do this then. That's the permanent code. It's not going to change. If you write that down or if you have it saved, you should be able to pull it back up on your browser. All right, here we go. Here is our question for the day. This is the review of the how to balance a redox reaction. Don't mind what it's saying there about the basic method. I'm going to show you that one last step here in just a second. So let me pull this up, put this on a screen so I can make it a little bit bigger. I don't know why my computer is a little slow, but it seems a little glitchy too. I think it's because Callie's on here. All right, let me pull this back to. All right, now Callie, move you out of the way. All right, let's get started there. Okay, folks. So let's have a few minutes. Let's see if you can go through this process. Remembering, first step is you should try and figure out which element is oxidized, which element is reduced. You got a 50-50 chance. Generally speaking, it's not going to be those oxygens or hydrogens. We have a process for dealing with those. Once you split them up into the half reactions, then you go through the process of balancing the oxygens. And what element do we use when we balance the oxygens? Water. What element? What compound? What substance? It's water. And then we got to balance the hydrogens. And what do we add simply for those? Hydrogen ions. Then we've got to balance the electrons. And what do we add to both or to one of the half reactions to balance the electrons? Hydrogens. Nope. We add electrons, right? But how do we add more electrons? What's the only way we can add more electrons to balance the two different numbers of electrons? We multiply them, we coefficient them. That is correct. Then we sum them up, cancel out like terms. So if you don't have all 8 of your steps, please get those out. I just went over them with you, and let's get going on these. Let's try and see if you can figure out how to balance out these half reactions. I'll follow along with you on the board here, on the whiteboard. Beep, 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 beep. Beep, 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 beep. Oh, I should probably do this myself, right? Let me go get a pen and paper so I can do this myself. I'll be right back.
How do I get a piece of paper? Oh, no. Where is the brokers? There, okay, I got it. Let me.
And if you're unaware, those dashes up here, that's actually a -1 is what that's implied right there. For whatever reason, chemists get a little lazy at times and don't write the full -1 or +1 up there. They'll just put pluses or minuses. Okay. Good on that.
We're gonna end up doing it on conditions.
The ones that we talked about last time were the acidic conditions, were the non-basic. So I'm going to do one more step to get us to the basic conditions today after we solve this. So we go through the whole method the same way. Then there's one additional step that I'm going to show you today after we get done. Okay. All right, let's see how you're doing here. Aaron, you got those half reactions established. You're doing well. Good. 360, 60. Xavier, your number of hydrogens is off. On the top one, you didn't count quite enough hydrogens. Recount the left side so that you can balance it on the right side. Andrew. All right, Andrew, man, you got it going on that first half reaction that you're writing there, balancing it with the waters. Good. Good start. Then Neil, yes, you got the right half reaction with the number of hydrogens on yours. Good. That's a great start. Charlie, you're trying to do this all at once. You have to break it up into half reactions. So not quite got the concept yet. Clay, that's fine. The answer is not right. So Clay, I don't see where yours is either. You're somewhere off on yours. So we'll have to follow up here once we get going, see how it goes. Your numbers or your chromiums are not correct, nor your waters. Drew, your number of electrons is too many somehow in there. So we'll have to check that one here in a second. All right, so Dylan wasn't here to see how to do the rest. Okay, so we'll catch you up eventually. Then Eli, just keep working on getting those split into half reactions off the air. Let's see. You've got correct number of hydrogens and electrons. Good, moving along. Hayden, let's see. Got the wrong number of hydrogens and electrons then, Hayden, so we'll have to help you out here in a second. Kate. Good. Just got to work on those electrons for that second half reaction. I'm sure that's what you're working on right now, but everything looks good, Kate. Kaylee, you've got it good with the correct hydrogens and electrons. Going well. Liam, same thing, got it going correctly with the correct number of hydrogens and electrons. Liz, wrong number of hydrogens. Lucas. Still going. Barbieri, you got the final answer here. Let's see what we got. Hi, Hanana. Yeah, that's the correct final answer, Lucas Barbieri, or Luke Barbieri. Wellerman, still going, I see. At some point, we'll get an answer hopefully in there. Missing your waters in there, Maya. So follow those steps and it will guide you through the process. You've got wrong number of electrons and wrong number of hydrogens, Natalie. on your half reactions. So we'll work with you here in just a second, try and get you built back up. Electrons got to be added in, Owen, on yours.
Oh.
Patrick, you're good on yours. Yours is in the right direction. Good.
Oh, yeah. Okay.
Same thing, Alfaro. Yours is in the right direction. Good. Yours got a little bit out of hand. Visione's got too many hydrogen on those initial steps. Too many hydrogens and electrons. Eden, let's see how you're doing. Too few hydrogens to balance yours out. Your hydrogens on your left side did not work out for the chlorides. Everything else looked okay. It's your electrons you haven't balanced yet either. All right, Zachariah, let's see, last person, give some feedback to reducing. Yes, but you are missing out your steps with water and hydrogens. Okay, let's go over this. All right, so here we go. First step in this process is to figure out who has been reduced, who has been oxidized. Now, here's the truth of this, though. As long as you get a clear indication that I've got chromiums that need to be balanced and I got chlorines that need to be balanced, you really don't need to worry about what the charges are. That's a separate skill. I will, at some point on the test, ask you to assign what are the oxidation states. We can practice that right now, but that's not a necessary skill. I could look at this and say, okay, these chlorines are going to need to go together. That's just the way that these types of reactions work. I will look at this and say, oh, well, these chromiums, they're the ones that are going to make up the second half reaction. So that's where I will make my stand with those. Now, that said, I can go ahead and I can assign the fact that this oxygen has a -2 for a sum of -6, meaning that this chlorine has a +5. Over here, it has a -1. So therefore, I can see that that's clearly one of the elements that has become more negative that is being reduced. I can then look at my hydrogens, +1, -2. That's a +3 then over here for this chromium. Over here, this is a -2 with a sum of -8, making this a +6. So this one clearly also is my second half reaction. It is being oxidized. It's becoming more positive, +3 to +6. So that's its own separate skill, but that's not necessary. Again, all you need to be able to do is to separate this into half reactions. Just look for the elements that aren't oxygen, hydrogen, and see if you can figure out that these are going to be the two that where we'll split them and make half reactions. Then, next step, step 2 says balance anything that's not hydrogen or oxygen. Well, that's the chlorine, that's the chromium. They are balanced, so we don't need to touch those. Step 3 says balance the oxygens. Oh, by the way, are these steps, would someone look on the cheat sheet and see if I have these steps? Are they on here? They're at the bottom of the pink sheet. So if you are unsure, you're like, well, I don't know where he's going with this. I have all the steps laid out in the cheat sheets, the pink colored pink. So you'll have those available during the exam. All right. Next step. Step 3, did I say? 4. I don't remember where we're at. We got to balance the oxygens. That means I have to add oxygens. Notice there are 3 oxygens. Some of you just put 1 water down here. We got to put 3 waters because I have 3 oxygens. Same story down below, and some of you only looked at 1 of these. Did I only look at 1? No, I did this right. Notice that there are 4 oxygens on the right. There are 3 oxygens on the left. That means I only need to add 1 water because we're looking to balance the oxygens on this step. So if I look here, I have 3 oxygens plus 1 would give me 4. I have 4 oxygens over here. So everything's balanced. Now the next step, step 5, I think, it's telling us to balance the number of hydrogens. So I look here and I have 6 hydrogens. So I will need to put 6 hydrogen ions on the left. I have a total of 3 hydrogens plus these 2, that's 5 hydrogens. So I would need to put 5 hydrogen ions on the right. Again, one sign that you're doing this process correct is if you have the hydrogens on opposite sides. That's a good thing. If you have the waters on opposite sides, that's another sign that you're doing something correct. The 6th step asks us then to add up all of the charges and make sure that they are balanced on both sides. Now, they don't have to equal 0 because that's what's going to happen over here on the left side. The sum of all the charges over here is -1 because the charge of water is 0. Over here on the right, my charge so far is +5. 6 minus 1 is +5. So I've got to make +5 and -1 equal. So how many electrons would I need to add to make it equal to -1? Go ahead. Yeah, I got to add 6 electrons. Now, it doesn't always work out that the number of electrons and the number of hydrogens are equal. But in this case, that is the case. That is the scenario. Down below, do the same thing. My charge sum over here is 0. Both of those compounds are 0. But over here, I have a sum of +3. -2 plus 5 is +3. So I've got to make the left side E0 equal to the right side +3. So that means this time I'm going to add 3 electrons. So again, here's the scenario where the hydrogens are not going to be equal to the electrons always. So be careful of that scenario. Now I have step 7. I got to make the electrons equal. The only way to do that, I can't just add more electrons because then that wouldn't balance out the rest. I wouldn't know where those charges come from. So the only way to balance them is by adding a coefficient. So I make everything on the second half reaction multiplied by 2. When I do that, that will make this a 2, that will make this a 2, that will make this a 2, that will make this a 10, and that will make this a 6. Well, those electrons are now going to balance out with one another. Why do we even have to? Am I the only teacher that stands? Everyone else? Okay, good. Okay, so I'm not. Good. Everybody stands? All right, so we should just throw away the chair.
You'll stand up and then like have to press.
He's a manly man. I can't compete.
Mr. Garrison,
Si, senor.
would it work the same? Like, would it still simplify down the same if you multiplied like the top half reaction by 3 and you multiply the bottom one by 6? It's still simplify out.
It would, but then you would have to reduce everything.
Yeah.
Yeah, because just like any good balanced reaction needs to be in the lowest common denominator. So yes, it would balance out and you could do that. That would be fine. But when you got your final answer, if it were 2, 6, 4, 2, 6, 4, you'd have to reduce those all by dividing by 2. So you could do that. But it's just an extra step you'd have to go through. All right, last step. Cancel out like terms. I've got 6 electrons on both sides. I have 6 hydrogens and 10 hydrogens. That means I'm going to end up with 4 hydrogens. My 2 waters are going to cancel out with one of the waters. I'm sorry, with 2 of the waters over here, leaving me with 1 water. This is my final answer. Now, if we want to rewrite it, that's perfectly fine. On the test, I'm not asking you to rewrite it. I am merely asking you to write somewhat legibly so I can see where your final answers are. If you do like I do, I just circled them there, and that's my final answer. This is how to balance a redox reaction. Now, here's the last step. Notice what the question states up here at the top. This is in basic conditions. What do you see in your final answer that tells you a contradictory piece of evidence? What does that mean if it's got H's here? It's an acid. All acids have free H's. That's what makes them dangerous. So we are going to add one more step. How do we do this? we add 4 hydroxides to both sides. So now my final answer, final answer, when it's in a basic condition, is I'm going to eliminate these hydrogens over here by adding 4 hydroxides. But if you do that to the right side, you got to do that to the left side. So my final answer would be 4 hydroxides plus ClO3 minus 1 plus 2CrOH3 produces Cl minus 1 plus. Now, notice this. What do you get if you add 4 H's and 4 OH's? What is H plus OH? It's H2O. So we actually end up with 5 waters on the right. And that's it. That's my final answer. So that's not a 40 over here, by the way. Make sure you know that. That is for OH. So that's the final step, is if your answer ends with H's, that's an acidic, and that's what most of what we've been practicing has been dealt with. But if it asks for a basic condition, the final step is to add the same number of OH's to both sides that you have of the leftover H's. If you didn't have any H's, it was already in a neutral state, so you wouldn't have to do anything. But that's not going to be the problem that you get. All right. Joy. All right, here we go. Here's what's going to happen. Since KG did not join us, I am not going to waste the time to go ahead and teach up the or talk about the project. That was the plan, was today I would introduce the project, give you the time next time. So I'll just save that for first thing tomorrow. We'll do a quick warm up over what I'm going to teach you right now, and then we'll jump into, well, we can't even do that. I need to give you all the time. So we're not going to do a warm up next time. What we will do is we will just jump into the project information and get you started on it with your team. Yes, sir. Ben Neal. Do what? What?
What about King George?
That's Callie Garrison, the other King George. What's up?
Do we need to choose our groups?
Yeah, you can choose your groups. Yeah, you can choose your groups. By the way, if you want to get a leg up, though, I will allow this. In your email, do not sign up now. Do not sign up now. Do not sign up now. I will give you the sign when you can sign up. In your email, you're going to get this Google Doc, Google Sheet, and you can put in your group members, and you can choose what topic you want to talk about. So it doesn't matter, and don't override anyone else. Don't be a jerk about this one. But we can fill this one in, and we will do that here shortly. We're not going to do it right now. I want to finish the topic, and then it'll be the last thing we do today. It'll be on your mark, get set, go. So if you want to have your up and ready, that's fine, but do not put your names in there, okay? Do not put your names in there. That would be cheating. That would be, does anyone know the story of the Oklahoma land run? You guys know that story? You would be the Sooner. That's right. You would be the cheaters. The boomers are the ones who wait. They're the rule followers. So be a boomer, not a Sooner. All right. Last topic. Let's get into net ionic equations. Boo. Monday. Better get that done before the end of the quarter. It's coming. All right. Let's see if I can find my topic here. Where are we at? Net ionic equations. Okay. Bless you. Bless you. All right. Quick discussion before we jump into net ionic equations. And trust me, net ionic equations seems like it's going to be horrible, but since we put the cart before the horse and went to talk about redox reactions, it's really not that bad anymore. All right. These are 50 things in my lifetime, some of these in your lifetime, which we no longer do, which we no longer need. As you are looking through these, I remember a silly date whenever you would call the movie theater and you would find out what the times were for the movies. You didn't, and if you were fortunate, your parents got the newspaper, which was a common thing, and you could look in there to find the times of it, but you could call up the movie theater and you'd have to wait for it and wait for it and wait for the movie that you wanted to find out if it was going to be available. How many of you still have a VCR in the house? Yes, Ben. Have you watched one on it? Have you had the pleasure of pulling out the tape and the tape's still stuck inside? That's the worst. It was the worst whenever that thing would happen. How many of you still have CDs laying around? Those are awful. Awesome. Have you seen the laser disc though? You have one of those too, Ben. Man, your family's just old school stuff. Man, that is amazing stuff. So it was like a huge CD, and it was before its time. It failed out somehow. The VHS, the tapes won out over the laser disc. I don't know. So it was like the predecessor of the DVD, of the CD things. Cassettes. Anyone do cassettes? Anyone have a cassette player? Man, what don't you have at your house? Do you have an 8-track too?
No.
Oh, that's where I got you. So the cassettes, I remember being in high school and it got to this point where you would have a stereo, if not just a boombox, and it would have 2 cassette players on top. You would put a blank one in and you would put your friend's cassette player in there and you put him in there and you would push play and you'd push record and it would do a copy over. So that was like the predecessor to, ripping off a CD, but it was illegal back then too. So how many of you still use a camera? Do you know how to use a real film camera? Yeah. Oh, wow. That's impressive. I've never even seen like a Gatling gun. Is that what you're shooting? People, you're mowing them down.
The blanket over your head.
Yeah.
The glass.
Do your parents still keep a phone book around? It's the silliest thing. That goes straight into the recycle bin when those arrive. Okay, so there was a day, these things called pagers. And they were the predecessor to the cell phones. Only the rich people could get the cell phones. So you get these pagers, and it just had like 12 digits on there, and that was just enough to put your phone number in there. Or if you got clever and you turned it upside down, you could spell hello, and then you'd send a second text. It's not really a text. You could send a second page to them and you could put your phone number. So it was like the predecessor to how to text someone. It was awesome fun. Or you could spell bad words too if you got really good. Think about that one. But you could spell those and send them back there. Do your parents still do photo albums? I don't know why. It's like, I try to tell my parents, I was like, it's on the computer. We can look at it anytime, Mom. I could put it on your TV if you want. How many of you have ever sent a letter? I know Miss Godfrey made you do a postcard. That was fun. They used to have postcard stamps. Did she bring you postcard stamps still? They're like cheaper than the forever stamps. Oh, well. All right. Well, these are things that no longer, the fax. Oh my gosh. I remember having to fax stuff. That was no fun. Well, these are things that over time we got rid of because innovations came along. They found to be necessary. And so what we're going to do today is we're going to do that exact same process. Now in redox reactions, what we are doing is we are repairing what the net ionic equation did. So the net ionic equation gets rid of stuff we don't need. The redox reaction put it back in. We put the water back in. Now, why would we want to get rid of the water? What does the water do in a reaction? Nothing. So that's the reason why chemists said, well, we can get rid of it. It only allows the chemicals to mix, which is important, but it really doesn't participate in the reaction. So we get rid of it. So that's our goal today, is to show ions and materials that are on both sides of a reaction that don't change their charge. Those spectator ions that we talked about, we're going to cross those out. So if we run on to a scenario where we find an element that doesn't change its charge, we are going to cancel it out. And again, in a perfect world, if we weren't with you, King George, sorry, we would have gone to the net ionic equations first and then gone to the redox reactions. But you guys already had the materials for the redox, so we decided to go there first. Now we're repairing our knowledge and we are improving it. We're going to talk about this as far as a net ionic equation. So notice what happened. The complete ionic reaction is the first reaction listed. And what happens is we canceled out the sodiums because the charge on both sides is +1. They're spectator ions. We also are able to cancel out the polyatomic ions. So those are larger spectator ions, but the charge of the nitrogen didn't change. The charge of those oxygens didn't change. So we canceled them out and we're left with the final answer. That's the goal, is the net ionic equation. There's only a few places where it gets a little bit tricky that you're going to have to follow along with me. I'll guide you through it. So here's a little bit of background. Here's a fancy word that just means to break apart. The word is dissociation. So if you've ever had that awkward moment in a friendship where you've decided, time for us to break up. If you're with a special someone out there and you've found another, why do people break up? 9/10 out of 10. Yeah, because there's someone else. So if they ever say what do they say?
It's not you, it's me.
That's right. Guess what it is?
It's you.
It's you. That's exactly right. Yeah, you've been through it. How many of you have ever been the dumper? Yes. Yes. I was always the dumpy. I was always dumped on. That's the best feeling. Yeah, it's great. Builds moral character. And they dissociated from me. They said, by the way, I need to grow, or I need to mature, or you're just too special for me. You deserve better. What's the best way to do it? If you're going to do it, if you're going to be mean, own it.
Ghost them. Rip the Band-Aid.
Own it. Rip the Band-Aid off is exactly right.
Do it in person.
That's exactly, and do it in person. Don't text that. Oh, just give them the opportunity to vent. Stand there and take it. It's part of life. People change their mind, and you're free to. I'm not saying you found someone in 5th grade, you have to stay with them. That's not true. Just let them have their feelings in their moment. All right. Dissociation means you are separating into its constituent parts. So if I have salt, NaCl, you put it in water, it's going to dissociate into a positive sodium and a negative chlorine. They're going to break apart into ions. So this is very specific. Dissociation is implied, or is telling you that it breaks apart into ions. So I can't take carbon dioxide and dissociate it because it's not ionic. It's 2 nonmetals. So it does not dissociate. So it has to be an ionic material, which this is taking us back. It has to be a metal and a non-metal. It has to be a positive and a negative, and they are going to split apart into those constituent pieces. It also has to have the presence of water. All right. Oh, and one other detail there. Do you notice that down the bottom? It's reversible. So, you know, Not a Surf. Anyone have heard of a band called Not a Surf? The Rules for Modern Dating, great song. And one of the rules of the modern dating song was that if you change your mind, you could get back together with them. Well, that's the same thing in dissociation. If you split apart into the ions, a few weeks later, you can come right back together and become salt, or Benifer, or Kali, Eli. I guess it would be spelled differently. Any others? Anyone else have a group name, a thruple name? No, or whatever. No? What am I? I'm Trent and Leah. Tria?
Or
Lent. That's what we are. We're Lent. So if Lent were to break up and become Trent and Leah, we could come right back together and make Lent again. Now, here's what happens when those ions dissociate. Just giving you a physical presence of what it looks like. It's not that they just break apart and they're just, you know, aimlessly searching, looking, and they could just longingly look at each other from across the room. I wish I were back with that person. No, because they're preoccupied. They are surrounded by water molecules. So it has to do with their charges and the fact that we learned that molecules are polar. And so what we have are these dipole moments that exist in water molecules. One side of the molecule is positive, the other side is negative, and they orient themselves so that the positive side is attracted to the negative ion. The negative side of the water is oriented towards the positive ion, and they surround them. They dissolve, if you will. It's one of the reasons why we can't see a solid crystal whenever it goes into water, is because it bends the light around all of these water molecules that are surrounding those ions, and it causes the light to bend around it, and that's why we no longer can see it once it dissolves. But there's a freebie for you, piece of information.
So when salt goes into water, no longer tasting salt, tasting bad and cold.
That's actually technically true. Yeah, you are separating them out. That is absolutely probably true. Yeah, it's interesting.
Water.
So I don't know what our tongue actually detects, if it detects the positive or negative ions. That's true. I wonder if it doesn't just detect the sodium. Yeah, because we don't taste the chlorine in our water very much. It may taste a little bit acidic, and I wonder if the combination of those is what. Anyway, here we go. Spectator ions. We've already learned that these are the elements that do not change their charge throughout the process. This is something that we learned about last time, so we know how to identify those. Just a reminder of that task. All right, so let's take a look at this balanced reaction. So we have already gone through the redox process, and we have a balanced reaction. What we want to do is write this now as a net ionic equation. That is our goal. So how we go about this process is we must learn how to appropriately write and split up all of these ionic compounds. The 2Cr, it's already written for us, so we don't have to split it up. By the way, what's the charge on that? When it's by itself? Zero, that is correct. The same for the 3 nickels on the right side. It's got a charge of 0. Very good. Now, well, goodness gracious. That's impressive. What is going to be our charge on the chlorines? We have a rule for halogens. What's going to be the charge of them? They are all -1s. That is correct. How about our nickel, though? We could do the Wonder Woman move and cross backwards to figure out the charge of that nickel. It's a +2. That's exactly right. We're going to need that. Same thing now for the chlorines and the chromiums. We cross backwards with the Wonder Woman move. Okay, so these are all skills that we already have in our back pocket. We're now just going to dissociate these ionic compounds into individual ions so that we can start looking who we get to cancel out. So here's where we assign those charges. I just did that with you as well. Now here is where we dissociate it. So notice what it was before. It was 3 nickel chlorides. Notice how I rewrite it, though. I don't write it as 3 Cl2s. When it dissociates, each individual chlorine separates into an individual ion. So we have a total of 3 times 2, which is 6 chlorines. Now, the nickels, they didn't do anything special. That's very easy for us. The other detail we need to understand is that anytime we dissociate these, the only reason why we do get to dissociate them is because they're aqueous, because they're in water. So we need to also apply the states of matter. And just as a refresher, you were given the states of matter of all of these, but you need to continue to carry them through. This aqueous needs to go for the nickel and the chlorine. This aqueous needs to be for the chromium and the chlorine. Here, you are given the state of matter for this chromium. You're given the state of matter for this nickel. It's just that you can't drop these off when we are writing an appropriate net ionic equation. So here we go. So here we have it all split up. Now we can look at this and we start saying, are there any spectator ions that haven't changed their charge? Go ahead, help me out. The chromium had a charge of 0. Over here, it has a charge of 3. So that will not get to cancel. The nickel has a +2 and a 0. So you don't cancel those out. But the chlorine, we have a scenario where the chlorine did not change its charge. It did not change its state of matter. So it really didn't do anything during the reaction. So we get to cancel it out. And our final answer, the net ionic equation, is what happens after you cancel out those spectator ions. It's really, now that we've gone through all of the assigning of states of matter from our balancing reactions, once we figured out how to assign the oxidation states, this is honestly not as terrible a process as it could have been had this were the introduction to redox. So in some regards, maybe this was a blessing in disguise that this came this way, and it's just one last step. All right, let's try and practice one of these. Let's see if we can figure some out. I've got a couple. Oh, by the way, if the question, which I believe tonight's homework does do this for you, it says, write a molecular equation, write a complete ionic, and write the net ionic. What do you notice is the difference between molecular and complete? What changed from molecular to complete? What did we do? Patrick, I'll go through.
There's all the molecules are separate.
That's it. That's it. Did you want to get, okay, chime in? Anyone else? Another term maybe to describe it? Go ahead, Clay. How'd you? They dissociated. That's the word we want. That's the key word. Yes. They dissociated, but they said they broke apart. The compounds broke apart. Now, which compounds break apart? The ones that are aqueous. Notice this. Oh, look at this little detail. This little gem. AgCl, it's a solid. It doesn't break apart. It stays as a solid. Don't break apart the solids or the liquids or the gases. Only the aqueous are going to be the ones that dissociate when they hit water. That's the very definition of dissociation. They get into water and they break apart into their constituent pieces. Very good. And then the final step, go ahead, Charlie, you can help me out. What's the difference between complete and net? What did we get rid of?
Get rid of the things that didn't.
Which are called what, Kate? What are the things that we get rid of called? That's it. The spectators. Those are the folks. Did you like that? Thank you, Ken. They are the ones that we get rid of because they didn't change their charge. So let's take a look. Which ones did we get rid of? Which ones didn't change their charge? You can chime it out, yell it out. Do you see it?
Sodium.
NO3. We got rid of the NO3. Was that you, Callie? Oh, I thought I heard some voice coming through the microphone. Lucas turned you up. Now tell me, Callie. Here's a test to see if she's got it.
I said the Na.
It's the Na. I swear to you, that does not sound like my daughter. I think it is. Chat GPT?
Yeah.
Did somebody just say I sound like a dude?
Sound like Kaylee, actually. I swear you two could switch. Your voices sound the exact same. Are you sick or something? I'm going to skip all these examples. We're going to jump to a real example, okay? We're going to do one example, and then I'm going to turn you loose, KG, okay? All right. Oh, I'm getting sick. Look at this, speaking of which. Look at this one here. There's only words. Oh, that means you have to go back in time. I was watching the Thanksgiving Day parade, and quite possibly one of the worst musicals that, I mean, I know these musicals join in on the Thanksgiving Day parade to try and sell themselves. So people want to go and see these plays in New York City. Oh my gosh. Back to the Future. That looked so dreadfully bad. It was so campy. But anyway, you're going to go back in time. I think is one of the songs. And we are going to figure out how to convert these names into formulas. And then we're going to write the other half, predict the products. Oh my gosh, this is like a perfect all-in-one type question from what we've learned in previous days of old. All right, here we go. What's the formula for silver? Yell it out, proud, loud. It is Ag. That is correct. What is the formula for nitrate? It is NO3. Does anyone recall what the charge of nitrate is? It is -1. So -1 and +1, those are canceling each other out. They're balanced. All right. What's the formula for, oh, by the way, it says a solution. Put this in your notes. If it tells you it's a solution, it is aqueous. That means it has dissolved in water. That is the definition of a aqueous material, is it is a solution. It has dissolved in liquid. Okay, liquid being water. We've got a second one, lithium. What's the formula for lithium? Li. What is the formula for bromine? Br. What are the charges of lithium and bromine? -1 and +1, crisscross applesauce, it's balanced. All right, it's aqueous. What type of reaction is this? Boy, this is old school stuff here, folks. Go ahead, Drews. It's the double swap one. What do we want to call that? Anyone else? It's a double replacement. It's an official name, but double swap is what they call it on the street. Yes. So we always switch the metals. So I'm going to put Ag with the Br. I'm going to put the Li with the NO3. Now, remember back, days of old, you had a solubility chart. You have a cheat sheet with the solubility chart on it. Tell me about the nitrates. Are they soluble or are they going to be a solid? They are soluble. They are AQ. All right, that was a 50-50 chance. I appreciate it. Here, let's try this one. How about bromines? What do we know about bromines? Are they always soluble? No. When's the exception? When they're with a silver, a heavy weight. This one is going to be a solid. This is flying past you at the speed of light, and you're saying, I don't know how you're pulling all this information. That's a red alert. You need to be starting your studying for the Monday test, folks. These are things that we've learned previously that are going to come back on the test. This is the expectation, is that you'd be able to do this. Exact same skill. All right. This is the molecular compound, because everything is balanced. There's one of everything. This is the molecular formula. Now we're going to, as Clayton says, dissociate it. Now we're going to break these apart. This is where great chemistry students make silly mistakes. Just be careful. It's AgAQ. And +1. We got to put the charge on it too. That's the worst. Forget these little details. And then NO3 -1AQ. Plus, same thing here. Lithium +1AQ. Plus Br -1AQ. All I did was I broke these apart into 4 individual pieces. That's the dissociation part. Don't forget, when it's a solid, you don't break it apart. So it stayed the same. So right away now, I am noticing there is a difference between the left side and the right side for Ag and for the Br. On the left side, the Ag, it's aqueous, but on the right side, it's a solid. So something changed. So it gets to stay. But the lithium and the nitrate, they may not be so lucky. So I'm going to do lithium +1 aqueous. And I'm going to do nitrate -1 aqueous. Now look at, this is my complete ionic. So this is, I will label these. This is my molecular, oh, misspelled. Molecular, this is complete. And then the last one is going to be the net ionic. So now we get to cancel out anywhere we have identical ions on the left and right side. So do you see any materials that are the same on the left that they are on the right? I got the same 3 people. Alfaro, help me out. What do you see is the same on the left that's on the right that we can cancel out? The lithium. I agree with you. That's a perfect answer. All right. Visione, help me out. What's the other material that's the same on both sides that we can cancel out? I apologize for my bad handwriting. That may not make it clear. Yes, the NO3 is absolutely correct. Great job. Because it's the same state of matter, because it's the same material and it didn't change its charge, they get canceled out of the net ionic. We get our final answer. You just rewrite this. Ag +1 aqueous plus Br -1 aqueous produces AgBr solid. This is the final stinking answer for what we're trying to accomplish. Yes, sir.
So in a net ionic equation, what are you putting in?
Do what?
Like,
yes, you are putting it in water. Yes.
So 2 aqueous, if you put 2 aqueous in this example,
they will cause a reaction and it will fall to the bottom and it will become a solid. We did this in the lab. We mixed 2 chemicals and it turned into that milky white substance. That's this reaction right here. We did it with 2 different chemicals, but it created a new substance and eventually it would have settled to the bottom. All right. I got to cut off here because I'm running out of time, A, and B, I don't want to belabor this too much more. So I'm cutting off King George and Callie. Good luck. Godspeed. Farewell. Thank you for your time. Bye. Right.